going to investigate friction, in particular the moving part of friction, kinetic friction, also called dynamic friction. So where does friction occur? Examples, if you're pushing or pulling an object over a surface. And what happens where those two surfaces meet? Well, if we look more closely, we see that things are actually rougher than they seem, the cardboard box and indeed the ground. So if we have a large TV in a box, what happens when you do that? Are some surfaces easier to push the object across than others? So just pause here to suggest easier surfaces and ones that might be harder. And what objects of a similar size to the TV in a box are easier to push over any one surface? So pause to do that activity. Good rule of thumb, the rougher the surface, the greater the friction. You'll come back with some unusual exceptions, but we don't need to look at those now. And it's the force between two objects that are moving over each other. NASA described them in pictures of lunar rovers and tires looking on the moon and testing on Earth. The resistance to relative motion between two surfaces in contact. And so we're going to investigate kinetic friction. And our moving object is a shoe, not being worn at the time. And our surface is going to be the lab bench. So we're going to pull a shoe across a lab bench surface. So how do you think you will do this? Write some bullet points, just brief notes of the rules or instructions you would need to follow to investigate the motion of the shoe across the bench. So pause to do that, and we will need to measure the force to keep the shoe moving. So we're going to use a spring balance, also called a Newton meter or a force meter, and it's all about extension of a spring and Hooke's law. The spring in the force meter, its extension is directly proportional to the mass. So we've got an empty weighing tray, one with some objects in it, and then one with more objects in it, and you can see the extension of the spring each time. And the extension of the spring directly proportional to the mass, the tension force upwards, and the weight due to gravity pulling downwards. And here's an older 150-year-old spring balance, and you can pause to read a little more details of that. So we're going to use the spring balance in two ways: holding vertically when you measure the weight of your shoe, the gravity acting on the shoe, and to measure the force of friction, you'll pull it horizontally between to get the friction between the bench and the sole of the shoe. And you'll take the reading. You'll see sort of the plunger within the force meter and the point at which you read the force that is applied. But you've got to keep the shoe moving. Now it has to continue to move steadily as you're reading it, and not accelerate and not change direction. So you can pause here and read closely about the procedure that you will apply. And so that's how you get your first readings. And then to continue, again pause, you're going to add masses, 500 grams at a time between readings. And then your data and analysis, and it shows here what you're going to graph and calculating the slope of line of best fit, etc. Pause for that one. You can either obviously do the experiment or use the data that follows, and choose one of the data sets unless you're told to do more, or if one is assigned to you, but please note the number of the data sets that you use, and process the results. You'll see more details in a moment. So here's data set 1, and below it shows the force of gravity, gravity acting on the shoe, the weight of the shoe, and then the items that are obtained for different trials. Different shoe here. There's getting the force of friction. There's getting the actual weight of the shoe. And just take the reading when the shoe is moving with constant velocity. And here's data set 2. Go on to another pair of shoes here, and data set 3. Some results being collected here, and then to process the data. So here we've got a graph where F, subscript F, is the force of friction, Fn is the normal force, the surface acting on, force supporting the shoe, and we want to investigate the relationship between those two items. But, got an arrow going to it, we only measured the shoe's weight and the pulling force with different masses in as well. So how can we relate normal force to mass and frictional force to the pulling force that we actually measured? Normal force, force acting upwards, Fn, pulling force as you're pulling the shoe in one direction, and the force of friction acting in the opposite direction, and then the gravitational pull, mass times the gravitational constant. But what we know is, looking at the red arrows there, that the normal force is equal to the actual gravitational pull, and we've measured that. And the force of friction, red arrows here, Ff pointing left, Fp, pulling force going right, they are equal. So we measure Fg and Fp, but they are in turn equal to Fn and Ff. So you can draw your graphs, you can look at the slope as instructed, etc. Go back to your data analysis to check that you do everything. And looking more closely, amplifying, magnifying what is between them. So nothing is completely flat. Some smooth surfaces look very rough when viewed with a microscope. And with our shoe, we do indeed have sort of almost corrugations on the lab bench surface at microscopic level, and indeed on the shoe sole. But what we discover here is that you have the force and the distance between the surfaces different when the force acting downwards is greater. And so with our shoe, that's when we're adding weights, gets closer together than it was without the weights in. So you're increasing the force required to pull the shoe across. And what is that relationship? You've looked at the slope. Is there a direct relationship in your graph? You can do more explorations. You can pause for this one, and you can just put in a search for PHET, friction, forces and motion, and there's a URL there if you want it. And so these are comparing kinetic friction between two surfaces. So which is the highest, which is the lowest? Do any of them surprise you? Why or why not? So pause to do that. And then when is friction helpful? When is it not helpful? So good friction, won't call it bad friction. And read those and add another item to each side there. And then a picture on the right, brake shoes. When you're cycling along, they're close to the tyre. Which list would you add brake shoes to, and explain why? Out of interest, friction inside Saturn's moon may provide power for hydrothermal energy. So interesting things happening within moons and indeed within planets as well. And for the curious, again, you can search friction versus temperature CK-12 or put in the URL to do that activity.
Hard to get into, so it's about that. It has 6.5.
8. No, well, it's like 8.
Point.
Let's say 8.3.
8.3. No, I think it goes higher. 6.7. Okay. Ooh.
Horizontal, down a bit, an angle, but you know, good enough for government work. This one. All right, so you're pulling it. That's good. Suggestions. So we'll rehash those for the reading.
Oh, that wasn't 10.2.
If she changed my grade to
And that is 14.4.
This is where you get extra points.
That's 12.
Yeah, 12.
Okay. I'll keep that.
Really heavy. Pull your feet. Bring your toes.
This won't fall because they won't go to each other.
Like 16.4.
Like 17.
Into after school.
Because otherwise I'll
How
post
you did the other one wrong?
whenever you can. I'll post it anyway.
Okay, thank you.
They're equal.
No.
They're equal. Why are they equal? Yes. Because what isn't it doing?
Because it's equal, because they're all like opposites.
Is it accelerating horizontally?
Yeah.
Really?